So in this class, let us discuss about Euler circuits and similarly Hamiltonian circuits. Okay. So initially, let us put this question. Let's say you have a graph with some number of vertices and some number of edges. Now the question is it possible to start at one point? Okay, start at one point and coming back to the same point by traveling all the edges. It means the question is there a simple path, simple circuit which traverses through all edges? So this is the question. Alright, so how about this graph? Do we have a solution? For example, I'd like to start here. Let me name these vertices 1, 2, 3, 4, 5. So can we have a simple circuit here so that it travels on all edges? First of all, do we have any circuit? There is a circuit, that is 1, 2, 3. But how about a circuit, a simple circuit which travels through all edges? Okay, I would like to start at 1. So if I start at 1, I'll go to 2, and then I'll maybe go to 4, and then to 5, then to 3. Yeah, but after reaching here is a problem. What is it? After reaching 3, if you come back to 1, okay, so you need to take this direction. It means now you are omitting this edge. So this is a circuit, but it is a simple circuit. But the problem is it is not traversing through all edges. All right. So let me do one thing. Let me start at some other point. This is 2, 3, 4, 5. All right. Now let me start at 3. Okay. So now this is how I'll go 3 to 1, and then 1 to 2, and then 2 to 3. Okay. Then 3 to, yeah, that's it. If I come back to 3 here, and if I leave 3, now I can't come back to 3 again because I utilized all edges which are incident to 3. Okay, so this way doesn't work. Okay, let me go in the other way. Two to 4, and then to 5, right? And then you can come back to 3, but here also you're omitting this edge. You're not traveling through this edge. Alright, so like that you need to try all possibilities. But how to know whether a graph has a simple circuit which travels to all edges or not? Okay, let me take one more problem. So how about this graph? So does this have a simple circuit which travels to all edges? Yes. Okay. So where to start and where to, what is the starting point of the circuit? So E, okay, let me start at E. So E to A to B, and then B to E. Oh my God. I'm writing E and C alike. Okay, let me make this. So this is C. And then E to D, and D to C, and then C to E. Okay, so you can see the path, the simple circuit, that is A, B, E, D, C, E. So the condition is you are not allowed to repeat the edge, but you can repeat the vertex. There is no condition on vertex. Okay, you can repeat the vertex, but you are not allowed to repeat the edge. So here edge is not repeated if you observe. Alright, the edges that we travel here are EA and AB, PE and ED and DC, CE. So no edge got repeated here. Okay, the only vertex may repeat, no issue. Alright, so it is very clear that this graph has a simple circuit, alright, which travels through all edges. So we have a name for this simple circuit. We call this as a Euler circuit. So what is the definition of Euler circuit? A simple circuit containing every edge of G. Simple circuit containing every edge of G is called Euler circuit. Okay, and similarly we have Euler path. What is Euler path? That is a simple path containing every edge of G. That's it. Okay. So the definition is a simple path. So you can look at some graphs which may have simple path but not a simple circuit. I hope you can look at this example. Do we have a simple path here for this one? So let me redraw this graph. This is the graph we have drawn there, right? The vertices are 1, 2, 3, 4, and 5. Alright. Now let us see what is a simple path here. Okay. So you are saying it is 2, 4, 5. Alright. 2, 4, 5. Then to 3. And then from 3 you can go to 2. And then 2 you can go 1. And 1 you can come to 3. So that is what 2, 4, 5, 3, 2, 1, 3. So it is a path starting at 2 and ending at 3 and which is traveling through all edges. Alright, we are not talking about vertices. Vertices may be repeated or may not be repeated. Alright, but it is traveling through all edges. This path is traveling through all edges. Not more than once. Alright, therefore it is a simple path containing every edge. Therefore this is an Euler path. So this graph has Euler path but not Euler circuit. Now let's take a directed graph now. So let's talk about, see these are, see here I have taken undirected graph. I have shown the paths here. Okay, it doesn't mean I have assigned directions. This is not a digraph. It is an undirected graph in which we identified the path. The path I denoted with this directions. All right. Now let me give you a digraph. So does this have an Euler path or Euler circuit? So do we have Euler path? See, it is digraph. Be careful. This is a digraph. Having an edge between two vertices, it may not guarantee a path from A to B. It may be that is a path from B to A. Okay. So if I think about circuit, let's say if I start at A, okay, you can go to B and then to C. That's it. You can't travel from C because C has no out degree vertex. I mean out degree edge. So you start at any point. For example, even if you start at D, max you can go to A, B, C. That's it. Okay, so there is no Euler circuit. So how about Euler path? Does it have any Euler path? No. Max you can travel these three. That's it. So you can't travel on DC. Okay, so the maximum length of simple path here is 3. We have 3 length path only. 3 length simple path. We have 1 length, 2 length, and 2 length, but the maximum length I am saying, maximum length of a simple path here is 3. But we need a 4 length path, 4 length simple path. Alright. So it is very clear that this digraph do not have any Euler circuit or Euler path. Alright. Now let us look at the theorems which gives necessary and sufficient condition for paths to have, graph to have Euler path or Euler circuit. Okay. Here is the necessary and sufficient condition for Euler circuits or Euler paths in an undirected graph. So you take an undirected graph, moreover undirected connected graph with at least 2 vertices. Then G can have Euler circuit if and only if each of its vertices has even degree. If each of its vertices is even degree, then only we can find an Euler path. Sorry, Euler circuit, not Euler path. Okay. Now let's look at this problem. Where is it? Yeah. Euler seems like so look at this graph G. If you look at degree of the vertices, let's write the degree sequence. The degree sequence here is, so this vertex has degree 3 and this has degree 3. I hope rest of the vertices are of degree 2. Alright. So now it has a vertex of odd degree. Therefore, now this theorem says that we cannot have a Euler circuit in this undirected connected graph. Okay, so it is very clear that using theorem we can say that there is no Euler circuit. It is in both ways, not just in one way. If you do not have an even, if you have a vertex of odd degree, you can say that it has no Euler circuit. Suppose if you find that all vertices are of even degree, then definitely there is an Euler circuit. But the question is how to find that Euler circuit. So we have an algorithm to find an Euler circuit here. Okay, so let me take one problem. With that I'll discuss. Okay. So look at this problem. Okay. So this is a named graph. Mahmud symmeters. So does this graph have an Euler circuit? So let's see degree sequence of this graph. What is a degree sequence? I hope you can see that B, E, D have degree 4. So 4, 4, 4. And even I, H, G has degree 4, 4, 4. And A, C, I, K, they have degrees. I hope F also has a degree 4. And rest have degree 2. Alright, this is degree sequence. So all vertices are of even degree. Therefore, by the previous theorem, you write the statement of theorem here, right? So a connected undirected graph has Euler circuit if and only if every vertex is of even degree. So hypothesis of the theorem is satisfied for this graph. Therefore, now let us try to find what is that Euler circuit. Okay. So now suppose if I start it like this, if I start drawing the circuit here, maybe starting at A to E, and then to I. Okay, let me just randomly try whether I get success or not. All right, then H to I to F, then to G, then to H, K, G, F. Wow, K, G, F. Yeah, and from F to D. Oh my God, here there is a problem. Now once if I come back to D, I'm not allowed to like I can travel on this path, but if I go to G, then there is no path from there because we already traveled all edges at G, right? So therefore, we won't get a simple circuit which travels through all edges here. All right. So I must let me do one thing. Now let us look at uh, the algorithm which identifies Euler circuit in this graph. Okay. So first, what you have to do is you start at any point. Maybe here I'm starting at A. You try to identify the simple circuit. There are no restrictions. I'm not asking you to. It has to travel to all edges. Okay. So just identify a simple circuit at A. So now can I say this? So the simple circuit here is at A, E, F, and then to I, E, A. Okay, so this is the circuit I have taken. I started. Oh, something is wrong. I can't travel on EA again. All right. So from E, you better come to B, and then B to A, you can go. So this is the circuit we identified. So first we travel from A to E, then to F, then to I, then I to E, E to B, B to A. Now let us redraw this graph by eliminating all the edges which are appeared in this simple circuit. Alright, so I'm redrawing this graph. So what we are doing is we are going to eliminate all the edges that appeared in this simple path. That picture looks very nice, but the picture that I am going to draw, it may look horrible. Okay. Um, so I need to remove AE edge. We have this. Is fine. Then AEF is not allowed. Okay, from here. Then this is there, and you're not allowed to draw this. Is also allowed. There it is in the moon shape, but here it is in, I don't know which shape it is. Alright. So now this is the graph by removing all edges that occurred in this circuit. Okay, did I take care of all? I removed AE, AB, EB, and EF. Yeah, EI. So we removed. Now you also remove these vertices, these isolated vertices, you remove it. Okay. Now look at this new graph. B, C, D, F, I, G, H, J. Now you try to identify again simple circuit in this graph that is going to start at one of these points that we used in the previous circuit. Okay, so it means you can think of a circuit which starts at E. Where is E? Oh, E became an isolated point, so I can't think of any because that is not available here, right? But you can think of a circuit which starts at F or I. Okay, you cannot think of J. Why? Because it is not in this circuit. You cannot think of H. You cannot think of a circuit which starts at K, and similarly G, and similarly D or C. We can think about a circuit which starts at B. Okay, so which one shall we pick up? So let me pick up B. You can pick up any one of it. It's not mandatory that you need to pick B. You can pick F or I. So now you think of a circuit which starts at B. So what is a circuit which starts at B? Let's grab the big circuit. Okay, so that is B, C, D. So let me write it here. That is B, C, D, and then to G, and then to K, H. After H, K, H. Better go to J, and then to I to again come back to H. All right, and then come to G, and from G you move to F, and from F you come to D, right? Where I started at B, I traveled along C and then came to D, right? Okay, now I reached D, and from D we can go to B. I hope we covered all edges. We covered all edges here. Okay. So now what you have to do is, now you identify this B in the original circuit, which is here, right? So now in place of B, what we will do is, we will replace this entire circuit. You understand? So in place of this B, we will replace this entire circuit. Therefore, now we will get a graph which travels through all edges. Sorry, we get a simple circuit which contains every edge of the graph. All right. Now let me write the resultant circuit here. So for that, let me take this. This is first one we have taken, and the other one that we have taken is this. Okay. Now therefore, now simple circuit or Euler circuit is nothing but, so that is A, E, F, I, E, B. Now in place of B, we need to write this entire guy, that is C. Okay, let me write with different color. So B, C, D, G, K, H, I, sorry, J, I, H, G, F, D, B, and then we need to continue the rest. What is it? Just A. Yeah. So this is how you can identify Euler circuit in a connected digraph if every vertex is of even degree. Okay. See, this procedure is not. I mean, you may not get a unique circuit using this procedure. For example, let me try it in another way. Okay, with the same problem, I'd like to try it in another way. So we can see the steps in which we constructed uh, the circuits here, and based on which we insert the circuits in the previous circuit, and finally we obtain the Euler circuit here. All right. So you try to identify these things using the circuits which are given here. Okay. The last one I considered here is that I that you can see. And before that, what is the vertex what is the one that we consider? That is yellow color one, right? So that is DFGH, that you can see it here. We need D also. Okay, a little bit of F, right? Okay, so this way you can simply construct Euler circuits. Now let us think about Euler paths. So let us see the theorem which guarantees Euler path in an undirected connected graph. So this theorem says that if the graph G has an Euler path, so the graph G has an Euler path if and only if it has exactly two vertices of odd degree. So if it has exactly two vertices of odd degree, then Euler path exists in that graph. So previously we looked at one example. Yeah, this one. Look at it. This graph does not have an Euler circuit because there is a vertex of odd degree. But when it comes to Euler path, yeah, it has an Euler path because we can identify two vertices of odd degree. All right, and the more interesting thing is that Euler path is going to start at odd degree term and ends at odd degree term. It starts at one odd degree and ends at another odd degree. For example, if I start here at A, if I want to identify Euler path, is it possible? Starting at A, let me try. A to B. Let me name this as C to C D E. Yeah. So first you may go from A to B, and then yeah, B to C, and C to E, E to D. Yeah. Now after reaching here, there is a dilemma. Okay. So after going to D, max you can go on one edge only. Even though there are two edges, once if you travel on this edge, then this edge is left over. All right. Whereas if you travel on this edge, then what happened? This edge is not taken care. Okay. So we are not finding a simple path starting at even degree vertex. But if you start at an odd degree vertex, that is you start at B. So you start at B and then to C, C to E, and E to D. Yeah. And then D to A, and A to B, and then B to D. Okay. So now this simple path is that is B, A, B, C, E, D, A, B, D. Okay, so you see the degree of the first vertex is 3 and the degree of the last vertex is 3. We started with an even odd degree vertex and ends with an odd degree vertex. Both vertices are not same. If both vertices are not same, if they are same, then it is an Euler circuit. But we anyway know it has no Euler circuit. Okay, so this is the Euler path. So now if you are given with a puzzle, now you can easily identify starting at one point, can you travel all edges or not? Suppose if you are asked to draw, so if you are clever enough, you must start with odd degree vertex. Okay, if you start with even degree vertex, you cannot end your journey by traveling all edges. Okay, now let me take an example here. So which of the following graphs have Euler path? The question is only that we can easily tell. They are not asking us to find the Euler path, right? So here for the first one, there are two vertices of degree 2 and two vertices of degree 3. Therefore, there are two vertices of degree odd degree. So this has an Euler path. So how about the second one? So let me write the degree sequence here. So the degree sequence for the second one, let me just identify the odd degree terms. If you find more than 2, then we are done. That's it. So you see the degree of B. The degree of B is 3. And degree of D is 3. And what else we have? No. So its degree is 2, right? And its degree is 4, and its degree is 4, and its degree is 2, and this degree is 4. So the degree sequence here is 4, 4, 4, 3, 3, 2, 2. Yeah. So we have two odd degree vertices. Therefore, there is an Euler path in G1, G2. Okay. So it has an Euler path. Next, let me think about the next problem. So how about this? Can we apply these to multigraphs? What is the statement of the theorem? So here the hypothesis is G be an undirected connected graph with at least two vertices. That's it. So you can take multi-graph also. They didn't say simple. I mean, the graph must be a simple graph. Okay, if it is only applicable for a simple graph, then they would have mentioned that. Now let's do one thing. Let us think of a multi-graph now. As you asked the question, just let me draw a multi-graph. Yeah, I'm taking an example of the multi-graph. So I'm okay. This is 3 degree. This is 3 degree. Yeah, and these two are 2 degrees. Degree of A and D. Okay, degree of D, A and D are pendant vertices. They are of degree 1, 1. Sorry. they are pendant vertices, right? Okay, let us do one thing. Let's establish a connection between them so that what I said it becomes correct. So A and D are degree 2 vertices now. Okay. So now I hope we can get it. So B to you travel on E2, then to C, then you travel on E3, you come to B, right? So E2, E3 are over. We traveled on it. Next, from B you travel on edge E1 and you come to A, and from there is edge 5 also. So you travel on edge 5, you come to D, and from D you travel on edge 4, you come to C. Yeah. So we got it. Without connections we want. What do you mean by without connection? Connection? Not connecting A and D. If you do not connect A and D, then what happens? See, then the degree becomes 1, no? The degree of A and D becomes 1. Now the number of odd degree vertices here are 4. But theorem guarantees an Euler path if you have only 2 odd degree vertices. The rest of the degrees must be even. You understand? So for this it is not possible. There is no Euler path because number of vertices of odd degree are more than 2. Not exactly 2 here. Okay, there are 4. All 4 vertices are of odd degree. Okay,